Alright, time for another draft physics video presentation. Such. Alright, so Farley, the only commenter, so just trolling bullshit. But now and then he brings up a valid-ish point in terms of a subject worth conversation. So let's understand that this is all an argument about theory. You know, how the universe works. And you can even go to subjects like light, and they really don't have a theory of why light reflects, for example. I mean, they can't explain to you, here's the photon, here it goes in, here it reflects. And they can't explain to you any of the processes that take place that constitute that reflection. And the same is true for this energy thing. So, as has sort of been illustrated or pointed out in a vague sense, we're basically talking about two ways of calculating how much energy something has, whatever word you want to use, for the fact that in the universe things will interact, and that interaction has a certain amount of oppositeness to it. This thing has a vector going this way, and this thing has a vector going that way, and those two things are combining, and there's a consequence. And the point is that we would agree, most people anyway, that the total energy in the universe is conserved. The argument is how you convert these things into heat and different things. So I could use the example like I could take two steel balls and I smash them together. Now if I don't allow them to freely bounce off of each other, and I actually bang them into each other with my energy and then my force holding them together essentially, and I put a piece of paper between them, they'll burn the paper. They'll just burn it. There'll be so much heat, it'll burn the paper. Now if I just take the two balls and let them bang into each other, they won't burn the paper because they'll bounce in the opposite directions. So the energy does go somewhere, where in the other case the energy is forced to bounce around inside between the two balls, and it goes back and forth a few hundred times or a few thousand or a few million and burns the paper. So it's a very subtle difference. So a lot of this gets more complicated when you take it out of a simple system and you make the system more complicated. So I will eventually get to a Professor Lewin video that it doesn't help either side. It just makes for a complex circumstance that requires a better answer than I'm probably going to provide, and they certainly can't provide it either. So anyway, the fundamental dispute about the invalidity of NV squared, the idea that the energy is represented by this silly formula, invented by Leibniz and defended by silly French people, and then contrived into a mathematical equation. So anyway, so in the Farley comment he says, if an 8-pound bowling ball, so he ignores the fundamental argument that the 8-pound ball going twice as fast as the 16-pound ball, there's no evidence it knocks down twice as many pins. So he ignores that argument where he's found to be lacking any evidence for any of this double the energy, the free energy type formula that it represents, and instead gets into this other subtlety. So if an 8-pound ball going 16 miles an hour hits a 16-pound ball, how fast would both balls go after impact? Now there is a formula for that. I don't know how, I can't say how, under what narrow circumstances it's actually true. And so that's the trick of it. Okay, so I'm going to show an example where Professor Lewin essentially does the experiment, but the balls have springs on them. So that complicates, because the springs are going to be moving with the objects and all that kind of stuff. So anyway, all right. So I state these reactions aren't what's under dispute. That is, the velocities created are not being disputed. How much energy those velocities represent is the part being disputed. So we're not really disputing how fast something leaves and how much something weighs. We're disputing whether the fact that it has more velocity means it has more energy innately. that you square this velocity thing, and so lighter things have more energy because they're moving faster. Kind of nonsense. I believe the answer is something like an 8-pound ball bounces off at 1/3 the velocity, and the 16-pound ball moves away at 2/3 the original velocity. Now, if you think about 2/3 on something twice as heavy, that's more momentum. But that's why the other thing is bouncing off. See, the other thing's going this way. So again, if you go back to a space analogy, then it can make sense, because you have a certain amount of momentum going that way initially, right? So you add a little extra to it, and the other side of the ship is sending something out going this way. So the 1/3 you sent this way is the extra 1/3 that's on this one. So in a sense, you still only have the original momentum in this direction, because the reflected energy is compensating for the extra velocity that you gave the heavier object. But in fact, there is now more momentum going this way. Now the catch is you have more momentum going that way. And so, like I said, if you were using it in a spaceship, you'd still be okay, because all you'd have was the initial energy this way. If you had a spaceship and you bounced something off of it, and the bounce caused a piece of your stuff to fly off, okay, that weighed more, okay, and it was traveling at 2/3 the original velocity of this thing. Well, if it's also going to make this thing that the mass became part of this mass, and it shoots off this other piece of mass at 1/3 the velocity, that's going to be the same as the extra. And so the net product is just going to be that a piece flew off this way and a piece flew off that way. But anyway, that one probably needs to be drawn. So he says the momentum equation doesn't answer that. Well, the mv squared doesn't answer anything either. You have to do different math or different compositions, different theory to explain interactions. The interactions really don't have anything to do with momentum versus mv squared. The interactions are what they are. That's, like I said, not the dispute. The dispute is that you say, fast things innately have more energy, which isn't true. All right, well, anyway, this led to him posting to really, well, whatever. So one link is just to a math page, and it has this, solving systems of equations, simultaneous equations. So you have two equations with two variables that you don't know, and therefore you can solve for the two unknown variables because you can use the two different equations, blah, 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 blah. So it says here, if you have two different equations with the same two unknowns in each, you can solve for both unknowns. There are three common methods of solving: addition, subtraction, duh, okay, substitution, well, there's your problem, and graphing. My whole argument is with your substitutions. So because in one circumstance, let's say you have a circumstance where the velocity ends up equaling the distance, and that the distance in meters will be the same as the velocity in meters, or the velocity ends up being 2 times the distance in meters. That doesn't mean that in all circumstances velocity equals this 2 times the distance. So the problem is with these derivatives, doing this to equations, is that if you have two equations that aren't matched in terms of the circumstance under which that's true, like for example a constant force like gravity, and you start applying it to some other circumstance. So something that's true in gravity, okay, that is, if you want twice the velocity, you have to go 4 times the distance. That doesn't mean it's true, when trains are going down the track. So you can't use two equations that have completely different premises or universes of which forces are going to be involved in the interaction. Okay, when trains hit each other, it's not a gravitational equation. It just isn't. So my argument is yeah, that's fine. But my whole point is that you converted a distance into a velocity, and that's why you're saying velocity squared. So instead of multiplying the distance times the velocity, you decided to say, well, distance is the same as velocity, or you decided in gravity distance is 4 times velocity, or whatever the relationship is, and so then you've decided to do that to every equation, and you can't. That's where it breaks down. So that's my argument to your math. I'm still arguing your math is contrived. All right, so this is a classic experiment. I mean, Professor Lewin does a poor version of it. It's been done lots of places on the internet. So he happens to pick a physics girl video, which is sort of annoying just because he still hasn't dealt with the fundamental argument in physics girl's video where she says, I 100% transferred the momentum, and yet I created a bunch of extra energy. I spilled it. So I used the momentum to do a whole bunch of work. That is, I heated things and did things, and yet I transferred 100% of it, which is ridiculous, frankly. All right. So, but this gets to, well, this really doesn't, frankly. It's really not the same subject as the other problem of big things, little things. I mean, little fast things hitting big things. See, there's a, that's part of this whole thing. Is it gets a little complicated when you just bang a cue ball into an 8 ball, for example, and they weigh the same mass and they hit each other and one flies off and one stops. That's understandable. It's nice and simple. But as soon as you make the two objects different masses, either bigger or smaller, that's when it gets complicated. Because big things can't push small things faster unless you apply a spring, right? And then they can push the small thing faster because they can compress the spring and then move the object and then release the spring. So they can change the velocities. They can add more velocity. All right. But the idea would be is it shouldn't be allowed to add more momentum. But the trick is if it's sending something the opposite way, then it's really not more momentum. All right. But anyway, yeah, so I haven't played this yet. So I'll just do my explanation that I already have, in a sense, provided with the ping pong ball example, frankly. Okay, I mean, you bounce a ping pong ball off of a cue ball, put it on a pendulum. Professor Lewin did this experiment. And it bounces back with more velocity. Okay, so when you bang the heavy object into the ping pong ball bounces off with more velocity, okay, than the original object is moving. So the velocity is increased. And as I explained, it's increased because the ping pong ball is deforming into a spring. It's essentially a spring. So the stacked balls are really, you could just replace them with a stack of springs, right? So if you take a basketball, it dents. And then some other kind of bouncy ball, and then some other kind of bouncy ball, and then some other kind of bouncy ball, right? So they're all balls that can bounce, all right? That all are non-elastic, inelastic. Yeah, that's the right way to say it, right? You always have to think about it because they have the word backwards, essentially. Elastic means hard. Okay, so they're inelastic because they're not. All right. It's essentially the same, I would argue, as just having a big spring and then a medium-sized spring and then and then a tiny spring. So it's the same thing as just bouncing springs on top of each other. And because what you're really going to do is just take this total mass. So the mass, the little mass. So you're taking this total mass and that's your momentum. And so when you drop it, it's going to be the total mass is going to drop, same velocity. And the total mass has a certain momentum, okay, a certain amount of energy because it's a mass and a velocity, okay, and whether you square it or not is irrelevant to the point that you have a mass and a velocity, and that means you have a certain amount of energy going down. And then what's going to happen is after they hit the ground, the little one's going to fly off at a very high velocity, very big velocity. So you'll have a little mass with a very high velocity. And these all won't bounce their normal amount is the point. The basketball won't bounce as high as it would have, and this won't bounce as high as it would have, and this won't bounce as high as it would have, because they're all going to basically put their bounce into the little thing. So it's going to register most of the energy. It's going to go into the littlest object and knock it out. So this is how you just convert velocities, right? So there are systems, there are ways, you know, just like a pulley works and a lever works. I mean, a lever creates, you know, you take a, you know, if you make a lever, and it, you know, imbalanced balance and imbalanced balance. I guess I should make a point there. So, you know, tips on that point. The point is you can turn a high velocity into a smaller velocity, or vice versa. And so the same principle here. So when the ball's hit, this ball is going to compress, and then it's going to compress here, and this one's 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 going to compress here. So they're all going to store the energy when they hit in the compression of the objects, and then they're going to start releasing it. And so this one is going to release it into this one, this will release into this one, so this one gets this portion, and then this one's going to release into this one, and then this one's going to release into this one. So the springs releasing at their maximum speed, I mean, there's less weight above the basketball than below the basketball, right? So the ball hits the ground, there's less weight above it than below it, so the maximum speed at which the ball reflexes, it's going to throw this with that maximum velocity that it can throw this much mass. And then this one's going to throw with this much mass. So the mass is getting smaller and smaller, but the throwing arm is the same. The energy to push is the same. So if you have a big mass object is going to be converting essentially its spring energy into the smaller object. However, you know, yeah, that's probably, I don't know, the lighter object. So the speed at which it can push is going to be higher than pushing itself. If it was just pushing just its mass, it can't push, right? So it's going to be pushing against this total mass at the bottom, but much less mass as it goes up. So the first push from here isn't going to be very fast, but the push from here is going to get faster and faster and faster because there's less and less of mass on that side of the dent. So anyway, and that's going to cause the little thing to have a substantial part of the momentum. Now, whether it's 2/3 of the total momentum, right? The total momentum you went down with, you're not going to get back up because all of these are going to reflect. All of them are going to go a little bit up this way. So all of the rest of them are going to bounce, but they're not going to absorb much of the energy because most of it will go into the small object. So that's the explanation. Now that's not really an explanation in terms of explaining all of the dynamics of all of these atoms moving and why you can, you know, like say when you do reflect, say you throw something at something very hard, where's the reflection? Is the reflection, you know, say it has a back surface. Where's the reflection? Is it reflecting off the surface, or is it, how deep does it go and then reflect? Or does it bounce all the way from the back and then come all the way back to the front to cause the reflection? These are all valid questions for which I don't even have a complete enough theory to tell you exactly in every case what the right answer is. I'd say that in the case of photons, it certainly happens here. Okay, on the surface. But anyway, that's another subject. It's a subject that, again, it's not entirely related to the dispute over how to quantize energy. What's the quantity of the energy? You know, and is it Newtonian, mass is equal to velocity in terms of its importance, or is it Leibnizian, where somehow velocity is so much more important to energy than mass? All right, so this is only 3 minutes, so it should be doable.
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm going to try the golf ball.
The super bouncy ball.
On top of the bouncy ball, on top of the basketball. And then I'm going to explain how it's related to a supernova.
Well, that's really dumb, frankly.
Can you see that? Probably not. So here it is again. The golf.
So as you can see, this one bounced, this one bounced. They all bounced some. So obviously some portion of the momentum went into all of those objects, but you know, the one got most.
Golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that?
So it's only twice the velocity if it's 40 feet up. Well, anyway, we don't want to get into a gravity argument.
Not much energy. Let's simplify it to these two balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop.
So again, there's no potential energy. There's just gravity, which is an active force. But whatever. So you're throwing it into an active force. The active force is a stream. The stream pushes it.
As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you...
Right, so that's just the friction. So yes, you lose some of the energy to the different ways. The air resistance is probably even more of a problem for the basketball. The air resistance ate up more of the basketball than friction.
Combine them, the tennis ball goes higher than its dropped height. Way higher.
Right. And that's because the mass of the basketball is the mass being used to carry the energy, and so the basketball goes way less high because it gave its portion of momentum to the tennis ball, and it was able to make the conversion merely because essentially the objects are springs, and it doesn't matter to a spring. So if I compress a spring a certain amount and I put a heavy thing on it, or I put a light thing on it, the spring doesn't care. It's going to go as fast as it can push by its momentum those objects. So the spring can only fly up so fast. So there's a limit. I can't put something, can't put I don't know, a grain of sand on it and have the sand go 50 feet high or something, because the spring can't go as fast to create that velocity. The spring has a maximum amount of speed that it can reflex with. And the basketball and the bounce ball, the tennis ball, they all have a certain amount of, once you compress them, they have a maximum reflexive speed. And so depending on how much weight's on top of that depression will just decide how much velocity it can give. So the less weight that's on it, the more velocity it'll give, because the faster the spring will uncompress.
Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy.
Well, there you go. At least they got that part right. So it's not really storing elastic potential energy, all this kind of mush. You're just actually converting the momentum. You're actually moving part of the basketball into the basketball. The basketball has a system where it's saying, now I'm under more pressure and I have to push back. It's going to push back because it's under more pressure.
As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline, when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy.
Well, I don't know if it's exactly the same way, because the basketball is storing energy at both. So again, she's ignoring the fact that the tennis ball is deforming. The basketball is deforming, so both of them are deforming, and the higher velocity won't be experienced by the basketball. No part of the basketball is going to go at high velocity. Only the tennis ball is.
Energy in its compression and is able to push the
See, I mean, you can see the tennis ball push into the basketball. I mean, you could see it, but she's not talking about that. So, and that's the key part. And the tennis ball itself deformed, and so it's those the top part is where the real conversion takes place, is between the basketball and the tennis ball, because the basketball springs are big springs. They can't go very fast, but if you put something very light on them, they'll go much faster than they can push the basketball.
ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together.
Right, and that would be conservation of momentum.
Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And
not some, a gigantic percentage. Well, not gigantic, a substantial percent, in the sense that 2/3, 1/3, that kind of numbers.
Since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, up, and away. Now,
so it probably gains some kind of number, like it's probably going to be a number like 1/3 of the momentum of the basketball, that is, the heavy object that had a lot of momentum, is added to the tennis ball. Plus, you have the amount of energy the tennis ball gets from deforming. That is, it's going to go into the basketball. The basketball is pushing it back up, and then its own compression is going to push again. So there's 2 points at which it's. Let's see. So to compare it to the trampoline thing is just saying if I use somebody else to push the spring in, and then I push the spring, I'm just compressing the spring deeper. So it's not exactly the same thing.
Back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce.
So you can see the huge compression in this blue ball is really springy. So again, you could just think of it as dropping springs of different masses, and they do the same thing.
You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. Epic! Just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova.
So the thing I think to gain out of this is the fact that everything sort of has to be understood from the elemental level as explosions. That every interaction is really going both ways. That the energy is in, what's a way to put it? It's like the gun analogy, right? The gun is shooting the bullet out. Well, why is the bullet, why is this argument that they use where some people would say, if I don't have an end to the gun, that, if I don't have some thing to stop the explosion from going this way, that somehow the bullet's going to go faster. Well, it can't go faster because the explosion is just basically saying I'm sending actual physical objects in these directions. And the actual physical objects are only going in these directions. That's it. I can't make them go in another direction until I reflect them. And to reflect them means I have to absorb them and reject them. So that's the part that's the part where the physics is a little bit unknown. Is how does the matter know that you're not able to move it? That you're not gonna move all the atoms. And if you don't move all the atoms, then that means the atoms essentially are pushing back. That means you're moving them and they're moving back. And that's what the reflection has to be made out of, is somehow the fact that you didn't successfully move them means they're going to push back.
Supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a
Alright, so it just isn't saying much. So the less dense layers are not smaller than the actual little particles that are part of the initial explosion. So there's little particles in the initial explosion. They give their energy to big pieces. Then the big pieces, the basketballs, start converting their energy into little pieces again, because they're going to hit little pieces. So, it's more complicated than this. But it's just pieces hitting pieces. And the fact is the rules for the size differences, the mass differences between how the interaction between the pieces is the real physics. But the real physics is that you can't create free energy. So the real physics is saying Leibniz can't be right. Okay, this velocity squared stuff would end up just creating perpetual energy in a direction. I mean, perpetually increasing energy.
Super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually...
So this is all just stuff they make up, and so some of it's true, some of it's probably not, but they can't tell the difference between the true parts and the parts, they got right. Because it's really under-evidenced and it's way over speculative. Instead of just saying, our speculation is... just a few qualifying phrases somewhere where we sort of think, we don't really know, but instead, no, they just talk as if they proved it somewhere.
Touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you...
all the extra little pretty cool bullshit you can live without.
You try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets...
Duh! It won't work.
Amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
Whatever. Anyway, so I thought they got the little one, the 4, to work. And she couldn't even get the 3 to work? Whatever. I thought they played the 4 in the beginning or something. I thought they did. I guess it's only 3 there. They had a little yellow one at the icon, so I don't know. So I guess that one didn't ever happen. Anyway, it doesn't really matter. Probably not worth changing subjects, but I will switch. So I'll go to the Professor Lewin video that really illustrates, there's a trick to this, and neither side has the answer to the trick. But be back. Alright, should be back. So we have the cars again. Now on these he has springs on them, which probably isn't ideal. To duplicate elastic collisions. So they really should be just letting the metal things hit the metal things and see what happens, and that would be a better example. It's like the bowling ball example, right? I mean, there's lots of circumstances that change the circumstance. So if you roll an 8-pound ball, well, as already pointed out, right? Rolling is storing momentum, but it's storing it in the wrong directions, right? It's not in the velocity of the object. So if it's rolling, then it has more momentum than if it's not rolling, because it actually has some momentum stored in the angular momentum of the rolling. But it can't convert that into anything, in the sense that the angular momentum isn't easily captured into a direction, because it obviously is going to be pushing something the wrong way, the roll way, rather than the direction that you're trying to measure. So how you're measuring a velocity gets complicated. So anyway, so in this case you have the twice as heavy object getting hit by the lighter object, and they don't stick. Okay, so the idea is that it's free to bounce off. Now it's not just free to, because they have a spring on it. So what's really going to happen is the spring is going to move with the object, and that's the whole thing that complicates this, is the center of gravity of the spring is moving, and that's going to change the consequence. But anyway. Okay, so when he pushes it in, the theory is, so he has 1/3 and 2/3 written down here. So the idea is the initial velocity. So if we just said it weighed 10 and it was going 10, we just use those numbers. So it has a momentum of 100 and it has a kinetic energy of 1,000, right? 100 times, yeah. And then we say this thing weighs 20. The idea would be is, well, if it weighs 20 and I'm going to give it 2/3 of the velocity of the smaller object, it's going to end up having a momentum that's going to be 1/3 to faster, more momentum. It's going to have 1/3 more momentum than the object that hit it. Now, how do you do that? Because that's like free energy. And maybe in a sense it is. Maybe in this limited sense, this is a way you can multiply momentum in a direction. But clearly, if you did put it in isolation as a system, like I said, inside a spaceship, the spaceship's only going to really feel this because it had to give away that. So giving it the 1/3 back the other way undoes the extra third going this way. But anyway, it's a very interesting outcome. So.
Go. Okay.
I don't know why he panics to stop them and catch them and all that stuff. It's like there's stops on the end of the track. I don't know. Anyway, I guess he doesn't want them coming back and changing the time any. All right, so the initial one has the smaller the number, the higher the velocity. So this is the initial velocity is represented by this number. Clearly, the object that left is this number, 186. So the twice as heavy thing left a little bit slower, but not a lot slower, with 3/4 of the original speed. So technically, if I multiplied that out, I would find if this had a 100 momentum, this represents 130 momentum, 133 precisely, right? If we use that 100 number. And this one is the 1/3 number going back. So this is the 375 is the speed of the reflection back. So it's 1/3 of the original speed is the reflection. So you have a 1/3 extra motion in this direction and 1/3 motion in that direction. Now those two cancel essentially as energy, and you end up with just the forward motion in the momentum of the object. So it is conservative, but it's only conservative if you measure it as an entire system, and it has the appearance of being not conservative otherwise. Now, it doesn't matter whether I use the momentum formula, kinetic energy formula, formalization of energy. Both of them end up with a non-conservative appearance. So if I do the kinetic energy theory, then I lost kinetic energy, okay, because this number, the 186 number, will represent only 75% of, something like that, of the original momentum I had in the first object. So I lost energy by kinetic energy standards because it is less velocity. And so it does turn out to be, say if it was supposed to be 1,000 in kinetic energy, I only have 850. So I lost kinetic energy. So by the momentum formula, I gained momentum. By the kinetic energy formula, I lost kinetic energy. So neither one of them provide a satisfactory answer.
Now comes the real acid test. 1, 2, 3, 1, 8, 6. 1, 2, 3. And what is the last one? 3, 7, 5.
So now he's just going to multiply those numbers by the fractions.
And let me use my calculator. 3, 7, 5 divided by 3. I could have done that by heart, of course. This is 0.125. An amazing agreement.
So that's the percentage of the velocity. So again, it's 1/3 extra velocity. Degrade in velocity. And then the other one, which is T2, which represents the twice as massive. Yeah.
Amazing. Only 2% off, less than 2%. Now here, 0.186 times 2 divided by 3, 0.124. I can't believe it.
I could have just done 0.66, right? Anyway, so it adds up. This is true. He did the experiment. These are the velocities. So clearly, this has more momentum than the initial object in that direction. But, as stated, the fact is that matter was pushed this way. So the fact is that, yes, you have more this way, but the fact is, through the process, you released energy in the opposite direction. So, you didn't, the total energy increased in a sense. You can almost make that argument, but not the momentum. But it is curious. So I'll in the future ponder this and reflect on it, because in a sense I'd say this was a violation of conservation of momentum, because you now have more energy going in that direction. But as I'm stating, because he's using springs, I don't think this would happen with real elastic objects. But regardless, the point is that the impact is moving, and that's the part that matters, because the reflection is I don't want to get into the relativity arguments. That wouldn't be helpful. I'm just saying, if you did it in a spaceship, it all works out. Momentum still works as the explanation. But there's no denying the fact that, in absolute sense, like I said, you have a certain amount of energy, momentum going this way, and then the outcome is you have more leaving this way. The heavier thing is going faster than the amount of momentum it could pour in. It can only pour in so much momentum. Obviously it poured in more, but the consequence of pouring more and more was it lost energy that way. It disposed of matter going the opposite way. So the net product is you have more mass going this way, but you also have mass going that way. So it's how the total energy has to still remain the same. But anyway, so that's for our future video. It's just an interesting, just demonstrates that the elemental physics has that answer in it. There's, the fact that the little bits are all moving the speed of light and they're doing these exchanges and blah, blah, blah. In that physics, this will be fixed. So the problem is that we're not thinking in terms of that physics. We're thinking in terms of this medium-sized universe where, 1 second, which is, trillions of events on the nuclear level, we're not seeing the real universe doing its stuff. We're seeing a much slower, retarded kind of version of reality. And that's why this paradox, has an explanation. I'm just saying this really doesn't have anything to do with the subject. This is a separate paradox that really screws up either one. Both sides don't have an answer to this. So, mv squared doesn't make this make sense. So anyway, that's the point. I just want to make the point that this has nothing really to do with the controversy over how you define what a joule of energy is. This has to do with, understanding reflections, which is a whole different, can of worms. Anyway, all right, so that's enough of a video, I believe. So, till the next time and such and so forth and whatnot. This has been a Draft Physics video presentation and such.